There is a journey humanity has been dreaming about for generations. A destination we can see with our own eyes in the night sky glowing red. We call it Mars. For decades, we've been asking the same question. How do we actually get there? Because going to Mars is not about building a big, music, rocket and lighting the engines. It's a chain of problems. Distance, radiation, fuel. Some of these challenges are engineering, some are biological, and every one of them must be solved before a human ever sets foot on, music, the red planet. This is the real story behind the question, how will we go to Mars? Right now, Mars is approximately 140 million miles away from Earth. That's the average. The actual distance changes constantly as both planets orbit the Sun at different speeds and distances. At its closest approach, Mars comes within about 34 million m of Earth. At its farthest, the gap stretches to 250 million miles. This creates the first major constraint on any Mars mission, timing. The planets align favorably for travel roughly every 26 months. During these windows, music, the journey becomes significantly shorter and requires less fuel. Miss the window and you wait another 2 years. But even during an optimal launch window, the trip takes time. Current estimates suggest, music, a one-way journey of approximately 180 to 210 days, somewhere between 6 and 7 months. That's 6 months in deep space, far beyond the protective bubble of Earth's magnetosphere. Exposed to cosmic radiation and solar particle events. 6 months in microgravity where bones lose density and muscles atrophy. 6 months in a confined spacecraft with the same crew members isolated from everyone else on Earth. And that's just the outbound leg. A typical Mars mission architecture includes 3 phases. The journey to Mars, the surface stay, and the return journey. The surface stay must be long because once you arrive at Mars, you can't immediately turn around and come home. The orbital mechanics don't allow it. You have to wait for the next transfer window, which means staying on Mars for approximately 500 to 600 days, more than a year and a half. Add it all together and you're looking at a round-trip mission duration of roughly 900 days. That's 2.5 years away from Earth. So the question becomes, how do we keep humans, music, alive and functional for that long? Before we can worry about the journey itself, we need a way to leave Earth. And that means we need a rocket. A very big rocket. Music, the challenge here is mass. Everything you send to Mars, the spacecraft, the crew, the life support systems, the food, the water, the equipment, the return vehicle, all of it has to, music, be launched from Earth's surface. And Earth's gravity is strong. Escaping it requires enormous, music, amounts of energy. The rocket equation is unforgiving. For every kilogram of payload, music, you want to send to Mars, you need many kg of fuel. And that fuel has mass, which means you need more fuel to lift the fuel. The numbers spiral quickly. Current estimates suggest that launching a human mission to Mars will require a vehicle capable of lifting somewhere between 50 and 100 metric tons to the Martian surface, depending on the mission architecture. That's significantly more than any rocket currently operational. Enter Starship. SpaceX's Starship is a 2-stage fully reusable launch system, music, designed specifically for missions like this. The vehicle consists of a Super Heavy booster and a Starship spacecraft stacked on top. When fully fueled and stacked, the system stands approximately 121 music m tall, taller than a football field is long, and has a mass of roughly 5,300 metric tons. The Super Heavy booster is powered by 33 Raptor engines burning liquid methane and liquid oxygen. These engines collectively produce thrust exceeding 73.5 meganewtons, more than twice the thrust of the Saturn V first stage that sent astronauts to the Moon. The Starship upper stage is powered by 6 additional, music, Raptor engines, 3 optimized for seal operation and 3 optimized for the vacuum of space. In its baseline, music, reusable configuration, Starship is designed to deliver between 100 and 150 metric tons to low Earth orbit. That's enough capacity to support, music, a Mars mission, but only if the architecture is designed correctly. And that brings us to the next problem. Here's the issue. A fully fueled Starship has enough propellant to, music, reach low Earth orbit, but it doesn't have enough propellant to go to Mars. Not even close. The journey to Mars requires a significant velocity change, what engineers call delta V. You need to accelerate out of Earth orbit, cruise to Mars, and then decelerate to enter Martian orbit or land on the surface. Music, all of that requires fuel, a lot of fuel, more fuel than a single Starship can carry, while also carrying a crew and their supplies. So SpaceX's solution is orbital refueling. The concept works like this. First, you launch a Starship to low Earth orbit. This Starship is your crew vehicle. It arrives in orbit with mostly empty propellant tanks. Then you launch a series of tanker Starships, identical vehicles, but configured to carry only propellant, no crew. Each tanker docks with the crew vehicle and transfers fuel. One tanker after another, slowly filling the crew vehicle's tanks. Estimates, music, suggest it will take somewhere between 8 and 16 tanker flights to fully refuel a single Starship in orbit depending on the mission profile, music, and payload mass. Once the crew vehicle is fully fueled, it can depart for Mars. This approach multiple launches to, music, support a single mission is fundamentally different from how we've done space exploration before. It's more complex. Music, it requires many successful launches in a short period of time. It requires precise orbital mechanics and docking operations, but it's also, music, the only way to get enough fuel to Mars without building an impossibly large rocket. Music, the challenge now is proving that it works. Refueling a spacecraft in, music, orbit has never been done before, not by anyone, not at this scale. SpaceX is currently developing the music technology and a demonstration is planned for the near future, but until it's tested in space, it remains unproven. Once the Starship leaves Earth orbit, it enters, music, deep space, and deep space is hostile. Outside Earth's protective, music, magnetosphere, the crew is exposed to two primary sources of radiation, galactic cosmic rays and, music, solar particle events. Galactic cosmic rays are high-energy particles originating from outside our solar system. They consist mostly of protons, music, but also include heavier ions like iron and carbon. These particles are traveling at nearly the speed of light and can, music, penetrate deep into matter including human tissue. The estimated radiation dose for a 3-year Mars mission is approximately 900 millis. Music, that's roughly 300 times the average annual radiation dose on Earth. Exposure, music, at this level significantly increases the risk of cancer. It also increases the risk of cardiovascular, music, disease, cataracts, and cognitive decline. Animal studies show that exposure to high-energy particles causes changes in brain structure. Neurons, music, lose dendritic complexity. Synaptic density decreases. Memory and decision music, are impaired. Some researchers estimate that 1 in 5 astronauts on a long-duration Mars mission would, music, experience measurable cognitive decline. Solar particle events are, music, different. These are bursts of radiation released during solar flares and coronal mass ejections. They consist, music, mostly of lower energy protons, but they come in enormous quantities. A large solar, music, particle event can deliver a lethal radiation dose in a matter of hours, music, if the crew is unprotected. The good news is that solar particle events are somewhat predictable. They occur more frequently during solar maximum and monitoring systems can provide some warning. The bad news is that no amount of warning helps if you don't have adequate shielding. Traditional shielding materials like lead or aluminum are heavy and not particularly effective against high-energy particles. In fact, when high-energy particles strike heavy materials, they can produce secondary radiation that's even more dangerous than the original particles. So current research focuses on lightweight shielding materials with high hydrogen content, things like water, polyethylene, or advanced materials like hydrogenated boron nitride nanotubes.